All right, hello and welcome everyone to GLOBEBUSTERS, Season 14, Episode 14. Today we're going to be giving a Celestial Theodolite update and kind of give a brief review from the ground up, starting with the null hypothesis, etc., to kind of illustrate what I think is one of the premier proofs that the Earth is not flat, or that the Earth is not flat. Oops, that the Earth's flat. So we'll get into that here in a second. Let's see here. All right. Let me screen share.
That's going to be Eclipse somewhere by tomorrow, just so you know.
It's fine.
Yeah, you're toast, buddy.
You're
fired.
I'm leading into it now, or whatever. So let's see. Mute screen share.
There's somebody hate watching you right now whose day you just made, is all I'm saying.
I mean, inshallah, they have a good day because of it. I'm happy to be of service. All right. So, starting with the null hypothesis, this is an extremely important concept in how we argue and how the conversation, should continue, because a lot of what goes on in the flat earth communities is argumentation over things that are not mutually exclusive. And if things don't provide a mutually exclusive outcome, then it's not it doesn't really have any validity to it. So we often see things like long distance measurements or the proposal to build a structure over some terrestrial distance, etc. And all of these things lack a external reference for the measurement to be compared to. The most significant proof of the globe exists as positions of the stars and how they change when an observer traverses the ground. Now they try to frame it as like the motion of the stars based on that is mutually exclusive to the shape of the ground by merging the celestial and terrestrial sphere models that Shane's done a 3-part series on. So if you haven't seen how they use their conceptual models to navigate and make the assertions that the Earth is a globe, I highly recommend those videos, because it'll give you the baseline foundation to understand the difference between like a physical model, physical reality and a conceptual model. Can you use the conceptual model to navigate all around the ground, all over the ground? Absolutely. Is it going to be internally consistent? 100%. And what we learned from the history of the Chinese with their unit of measurement of a li being defined as an arc of the sky, they also had an internally consistent unit of measurement that they could use to traverse the ground and get actual distances to that were consistent with what they were using. And what we found in 2004 through an eclipse test, testing the way that the Chinese determined longitude, which determines the accuracy of how they were using their version of the celestial sphere. Well, in modern times, the accuracy was sub 1 degree, which is perfectly usable for celestial navigation. In fact, that was one of the threshold requirements back in 1777 imposed by the king, where they were offering a reward for anyone who could have their coordinate system be used in such a way that that two parties could circumnavigate around Great Britain with respect to one another and be within half a degree of accuracy. So and we know from the history of the Jesuits, as told to us by the Jesuits, that they didn't arrive in China until the 1600s. So all the navigation and maps and everything that were used and created prior to that were derived under the principles of a hemisphere of vision and the ground being flat. And the Chinese navigated in both hemispheres. They were actually the first people to map out the south. They got the GP for the circumpolar star Canopus, and then using that, they used the same 69 mile per degree latitude dependent relationship as Polaris to map out where they were going, and they used the two stars that lead the Southern Cross as a reference to where they could find to get the true south and all that, so that they could get their directional bearings. So none of what they assert in modern times is absolutely mutually exclusive. It's actually just two conceptual models overlaid, or one's put under the other one, but you only use one hemisphere at a time, because an observer only sees their respective hemi at a time, so everything in it is going to be relative to that. And that's how the entire system works. They just merged the two together and said that, and by binding it by time, where angles in the sky are determined by time, because the stars move at a constant rate, so that creates an angle change as well. So they base everything off of that, and that isn't mutually exclusive to any model, right? It does make a nice cohesive model, and it does a lot of observations could easily be explained by just simply saying, well, the Earth's a sphere, you're on the underside of it. That's how it works. Well, that's not how it has to work. That's how it works in one conceptual model based off of a bunch of assumptions that primarily make the stars and objects that we see in the sky physical. So it creates a reliance on a God's eye view physicality perspective to kind of even assert a unified motion for what every observer would see, and that's not the case here. But all we have are terrestrial measurements that we could do on the ground, but there is a mixture of the two that we could do that borrows from a concept called archaeoastronomy, which is where terrestrial features intersect, or I'm sorry, with celestial features. So in other words, like the sun rising or setting in a certain mountain peak range throughout the year, it's always going to rise and set in that certain range, and it's repeatable. It happens throughout the year. They can come back to that, and so using those intersection points, we can kind of draw some conclusions about the motion of the sky and what it's doing with respect to the ground. So, in the form of arguing with a null hypothesis for mutual exclusivity here, we don't argue a model based on apparent positions or conceptual things like that. We take it to a place where we're using occlusions as a physical process to make a geometric measurement with a timing interval, because we know the positions of the stars with respect to time will give us an angle. So we know when the star gets occluded, that will provide us an angle that we can work with, and we can reference the angle that we can reference that angle with the object that did the occluding, and we could see if they intersect. And if they intersect, then that we can determine whether or not there was actual drop over distance for that mountain peak. So to break this down, we start with the H naught, which is the thing that we're going to assume to be true. This is going to be that the Earth is a globe, that it's round. And then our null hypothesis, our H1, is going to be that the Earth is not a globe, it's flat. So there's two mutually exclusive claims here. The Earth can't be flat and round at the same time. So you can think of it as our H naught is less than or greater than 0. And then this our H is 0. So these are two separate things that lead to different conclusions here. So for the specifics of mountain occlusions and how we're using globe tools and globe units of measurement, etc., well, I like to think of it as we're testing an internally consistent system by using the occlusions and then referencing the object that did the occluding for the geometric angle relationship. So in this setup, the IV would be the observer distance to the peak and the elevation relative to sea level. And then that determines the geometric angle to the peak. And then we have the control, which is going to be the known elevation of the mountain peak, which is extremely significant because we don't we can't manipulate that. It's always going to be whatever unit of measurement it is. And actually, we're going to be coming back to the elevation of mountain peaks above sea level here soon with the story of old Al-Biruni, and then we'll lead into Eratosthenes, which is another classic example of how they can just use a simple trig relationship to establish a globe where there isn't one. But anyway, the dV there is going to be the occlusion angle time, and that's going to be dependent on your distance away from the peak. And so it's going to be dependent on a combination of the IV and the control there. So you can change your distance to the peak, which is going to change the occlusion time angle. So that's how you get that. And then we're referencing, this is entirely dependent on the intersection of the star to the peak. So that's how we break this down in terms of an IV dV control situation there. And then for those of you who aren't familiar, a refracted image or an apparent image is an image that's created on the boundary interface to another medium. So in the case of the globe, they would say that the refraction creates a homogeneous gradient that serves as the boundary interface for images to be refracted up or refracted down. And let's see here. Oh yeah, with that creates a the appearance of an image where the light rays don't actually converge to, because that's not the source where they come from. So when light intersects with that image, it doesn't actually cause an occlusion. And we can go over a brief example of that real quick here, kind of showcasing that. So what I'm going to show here is the street lights outside don't get occluded by the reflected images that are in the boundary interface of the glass window here. So we'll see the exact example that I'm talking about. And the only way that we could block that light source in the boundary area layer there is to move in such a way that the physical beam blocks the light source. So we'll see what that looks like here. I'll play this out real quick. All right, a quick lesson on the principles of the cell Theo. So what we're looking at here is you can see the pad. Oh, I shared it with no audio specifically because I didn't think I was going to do any audio stuff. All right, 1 second. I'll take care of that. All right, so this is on the principles of occlusion for the celestial theodolite and just occlusions in general. So what I'm showing here is the lamp outside here, and how it's distinctly different from the other lights that are being reflected into the window there. But what you'll see is that the apparent beam that's reflected into the window doesn't cause an occlusion when it intersects with the real light source out there, or even though that light source is reflected in there as well, but it's just not in much of a different physical location. But in any case, the light coming from it doesn't get occluded by the apparent object, because that's not where the real object is. That's not where the rays are actually coming from. But when I move in a way that intersects with the physical object, we no longer see the light source, and then we have to overcome the physical object to again see the emergent light. So same exact concept for the celestial theodolite and refracted images. So although you may be looking out at a mountain peak range and it looks smaller in the horizon, and the globe lads would like to say, well, that's due to physical drop over distance, because the mountain's kind of tilted away from you at an angle because it's going down in elevation because globe. Whereas we would say that it's just an optical effect. Oh yeah, and then they would also say it's refracted up a little bit, so they give, like, based on the distance, anywhere from 1 to 2 arc minutes of lift for celestial or terrestrial refraction. But as I was just showing here, that amount, that 1 to 2 arc minute difference that they would suggest, that's not a physical property of the mountain. That would never cause an occlusion. The occlusion has to be with respect to the geometric intersection point. All right. So we kind of went over null hypothesis testing, the importance of mutually exclusive outcomes, and just one real quick note to end on it. The null hypothesis method is used in a bunch of different facets of physics and finance. Like it's in all kinds of fields, but is what I found. But the most important feature of it is that it will allow you to come to a conclusion through deductive reasoning rather than inductive reasoning, which leads to infinite regression, because you just you keep ad hoc adding things to supplement your original premise. Whereas this it starts to rule things out in a conclusive manner. And there's 2 types of ways that you can rule things out. You can do the sophisticated nullification, which is where you would do like a statistical analysis to prove falsification. So if you take the black swan scenario where all swans are white, but you see the black swan, well, they just falsified it. Well, the sophisticated nullification would be, you would need at least like 3 black swans for statistical significance to show that it wasn't just an anomaly. There wasn't just a genetic DNA mix-up or something, some mutation that happened one time, some freak accident that caused a black swan. You need statistical significance. And then the other one is called naive falsification, which is just based off of ruling out the mutual exclusive outcome, like not doing the statistical breakdown of it for the significance, but just looking at it as like, okay, we have these 2 sets of parameters. Which one came out to be the truthful, or which one was failed? Which one failed to be falsified or substantiated? So, in that regard, that's how you move forward and produce a more cohesive way to get to the truth, in my opinion. And a lot of that is based on the philosophy of science through Karl Popper. Who proposed that. It made the point about the infinite regression that stems from inductive reasoning. All right. So now that we've got a cohesive framework to interpret this, we need to determine like what constitutes as a globe prediction, what constitutes as a flat Earth prediction. Well, to give a brief recap here, we're going to go over a single celestial theodolite measurement and how it applies, and then we're going to look at the broad spectrum of what was just put forward, where there was a new application that was put forward where you can use eclipses and the angles of the observers along the line of the shadow and the length of the shadow itself to do some basic trig to determine the altitude of the moon, which you could then consider that as the peak for the reference of how we're doing arctan rise over run to get the elevations for things. And so when we do that, we can make a congruent triangle with the sun and moon extending out, showing that the elevation change between the two is never more than, I think, 10,000 meters or something like that. It was, or it might have even been lower than that. I think it was like 6,000 meters. We'll go through it here in the PDF. But the whole entire globe model is predicated on physical elevation changes due to the curvature of Earth. The merger of the celestial and terrestrial sphere models facilitate explicitly that there has to be ground curvature. And one of the big, most significant things that we found during this whole exercise is something called the relationship between central angle theory and the celestial and terrestrial spheres. So for every 90 degrees of motion in the sky, that's represented by 45 degrees of it's represented by 45 degrees of drop. So it's from drop from the terrestrial. So in other words, the ratio between the two of curvature and drop in the sky is half gamma. Gamma is the central angle here, which is determined by these two intersecting points on the sphere. So we have observer H. This is where you're standing on the sphere, and this is where the mountain peak is. This angle here is proportional to the angle that would be created when you're standing on the mountain peak looking out, and what you would see for like the drop in the horizon. You could directly relate that angle to this and derive a radius where there isn't one, just based off of having the height of the mountain peak and the angle there. That's actually what Alberuni did, and we'll be getting into the circularity of that and the little a couple of assumptions that have to be made before you could do that. But he apparently derived the circumference of Earth doing applying central angle theorem. But in any case, in order for that to work, long story short, is that when we get into drop over distance, we can show that the doubling that amount will tell you how much the star dropped relative to you over that distance as well. So that's substantiated by using 360 times the distance over 2 pi r to get the full celestial drop. So that's what would describe. That's what would describe the star moving from this zenith position over to this position over here to get occluded by this mountain. There would be 45 seconds or 45 minutes of a celestial drop, and that comes out to be, if you convert that into meters over that distance, that would be 400 meters. Now half of that half gamma that we talked about earlier, that would be 180 times the distance instead of 360 over 2 pi r, and that 180 gives us that half gamma term. So the amount of curvature over this arc length,
directly relates to the equation. Wow, no way.
Yeah, man, where did I, notation, sorry. Here we go. Directly relates to that amount of curvature. So they're hand in hand to create the physical elevation change of the stars. Now, they're always looking at the apparent position of the stars, and they talk about how there's refraction with respect to the true position that's lifting it up or bending it down, what have you. But the fact of the matter is that star couldn't be refracted and have its position changed unless it was following a physical elevation change, like per their model. For us, we can invoke apparent, but for them, it has to be a physical change based on this relationship of curvature. The ground is directly related to the sky through this central angle here. And we can show that by taking the We have the true position of the star at the time of occlusion. So again, in stellarium and celestial navigation, etc., angle equals time. So if we know what time it is, we know the angle of the star. So we have this angle here. We could subtract the 27 arc minutes from this angle here, which is the product of the 360 times the distance over 2 pi r times Earth's radius, which gives you that 27. You subtract that, well, that equals the position of the star for the observer over that time difference. So it comes out to be 206, and we have the difference here for the globe celestial offset. So this is just like a sanity check to make sure that what we're doing is consistent with what the globe actually predicts and how it says stellarium works, or how it says that the stars move, rather. So by referencing this and showing, like, if this value ever goes any higher than arc seconds, which is a rounding difference between the two, then like we're doing something wrong. But if you go through the spreadsheet and you change peaks and different stars, you'll see that we exactly show that geometric relationship just fine. So in other words, we couldn't steelman the globe any harder if we tried.
But let's see. So to be clear, when Heffron put this method forward, he had deduced like the reason he became a flat earther not only through failing to falsify his null hypothesis, but he went through the math and he actually concluded that the globe is constructed in these mathematical equations. They take regular observations and then through this math that he was looking at, they turn that into a globe. And he concluded that therefore the globe exists only in these equations. So when we're saying 360 times the distance over 2 pi r, that's the central angle theorem. That's what we've been using the whole time. That is exactly what he came out with out the gate as the globe prediction was. We'll do, the flat Earth prediction, and we'll subtract the central angle theorem, meaning this drop over that distance, and that'll be the globe prediction. And all the globers were like, no, 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 but it was exactly the same prediction, exactly the same everything. And now they're like, yeah, but it's not right. And then, like the whole progression to get them to accept what we just went over is crazy.
Yeah, and then after it turned out that the math was equivalent, we're all arriving at the same place. It then just became about, oh, let's just let's nitpick on specifics of a measurement that don't matter. Let's focus on anything we can to invalidate the methodology rather than trying to produce like globe measurements. Did everything but that. So we have let's see, we'll get to that at the end here. All right, so following that basic treatment of how we're deriving distances and elevations, what we could do to for our null hypothesis and hypothesis predictions, we can do the arctan rise over run to the peak, which is just taking the difference in height elevation between the observer and the peak over the distance, and that gives you an angle. So that angle assumes no drop over distance. So that's just what the mountain would be, as if there's no drop over distance, irrespective of any optical compression where, like, okay, well, you calculated 233, but a regular theodolite measures 218. Yeah, our premise is that that's an optical phenomenon. That's why we use the occlusions, because that's going to provide an actual geometric intersection that's going to be relatable to an actual angle. So we start off with that for the flat Earth prediction. And then for the globe prediction, like Shane was saying, we do a little combination of central angle theorem, and we subtract that from the flat Earth angle. Oops. In the spreadsheet here. So for Pikes Peak, for example, we come out with 231 for the physical elevation with no drop over distance. With using central angle theorem, we come up with 13 arc minutes of elevation change, which comes out to be 200 meters. And if you do any sort of curvature approximation, hyperbolic or what have you, you're going to get the same 201 meters over that distance. So this method, like, it's not just an approximation, it's what it has to be over that distance as per how it relates to the celestial sphere and terrestrial sphere using central angle theorem. So this distance isn't something that can be like, oh, a Home Depot, or it's not big enough. It's mandatory. There's a mandatory 13 arc minute difference. And because
you can't Home Depot your way out of that one. Wow, you can't Home Depot your way. I don't know, a 201 meter drop. You just can't do it. That's true.
And because the angles are equal to time, this 13 arc second difference means that this occlusion intersection is going to happen at a different time. So what's the conversion for arc minutes to seconds? It's 1 arc minute equals 4 real seconds. So we did 13 times 4.
52.
Yeah, it's almost a minute difference in occlusion timing. So the globe would predict that the star has to physically get lower following that rate of 15 degrees per hour for the motion of the star to actually intersect with the elevation of the mountain, which is predicted to be at 217. So this is what creates the difference between our predictions. And as Shane just pointed out, isn't it miraculous that you could take central angle theorem drops, subtract them from the flat Earth prediction, and it's exactly what the globe predicts as physical elevation. Interesting relationship there. So yeah, so to continue on here, after we have the so we have our occlusion timing differences, and then when you go through the data, there are one measurement that is 2 measurements that are indistinguishable from globe and flat Earth, but we'll get into the specifics on how to analyze, but more specifically what we're interested in, rather than using the celestial theodolite at low angles where there's looming and lingering / actual refraction conditions that are affecting the measurements, we can use the eclipse that happened in 2024. And using that, we get angles that are much more much higher in the sky. I think it goes from a range of 19 to 70 or something like that. So we'll look at the angle differences here as we continue. But here's a brief summary of the longest distances that the celestial theodolite was used at. So going from shortest to longest was 8,804 meters. So that comes out to be about 4 miles, 5 miles, close to that. That was the shortest one. And then the longest one was North Peak at 130,000 meters. And that was, let's see, a little over half a degree for the angle. So that was, so this is the maximum distances and the mins that have been used so far. And then Brian came out and was like, yo, we're going to do 7,772,000 meters, which is basically, you can kind of think about it as going diagonally across the whole United States. That would be kind of the length of what's being put forward there. So the exact shadow length that was produced by the eclipse, we're going to take that as the baseline for our run to when we start to do some triangling here. So some notable cities that the eclipse passed through was Austin, Texas, Dallas, Texas, Little Rock, Arkansas, Indianapolis, Indiana, Indianapolis, Indiana. Whew, it was a tough one. Toledo, Ohio, and Rochester, New York. So we have the times here that what's the word I'm looking for? It's not prominence. When you see the thing happen, totality. So we have the times here for all of that. So looking at the motion of the sun and moon as they would describe the eclipse there for how it produces the shadows, this is kind of what we're looking at here for the intersection there. So that's the path of the shadow as it traversed here. And let's see. So what Brian did was there's a file on NASA that has the total length of the shadow and the observer angles to the moon at that time. So what he did was he just took the tangent of those angles times the distance of that shadow length, and he got which produces the elevation, the physical elevation or the rise. And what he came up with was a distance of 6,370,774 meters. So that would be the elevation of like when they talk about in the celestial and terrestrial sphere models, they'll often teach celestial navigation conceptually as you can think about you being the observer standing at the center of Earth, looking up at a hollowed shell, and the celestial bodies are fixed to the radius of Earth, spinning around you. This would be that this is that radius. So he derived like in other words, the limit of how we perceive these celestial bodies. This would be the elevation that it comes out to. And then based off of that, with the occlusion for the sun, we can get the elevation of the sun for how that worked out. But if you were to kind of think about this Let's see. So we know that they have everything mapped to basically to the simple relationship of 60 nautical miles per degree. Well, if you were to take the way that the sun and moon move, they don't quite follow the 60 nautical mile per degree relationship. That's why we get two different values for the altitude of the celestial sphere with these intersections here. But so another way to conceptualize it is that the moon moves at 59.13 nautical miles per degree rather than the 60. Um, and that'll be significant later when he gets into um, deriving the elevation and then comparing it to what they say for Kepler and Newton's laws in terms of the distances, because they obviously have an established distance of 300 million kilometers or 300,000 kilometers. So what we can show is that through the trig from the eclipses, that the only tenable distance would be the distance that works with celestial navigation, which happens to be the radius of Earth or the radius of our vision, depending on which belief system you adhere to. So here is a plot of the elevation change over all of those 6,000 data points. So what he's showing here is that there is no elevation change. This a uh, linear progression down to, I think it's 12 decimals or 11 decimals. So no elevation change for the sun and the moon. And what that means is the way that they conceptualize, with that central angle theorem, how I was saying earlier, they predict a physical that each observer, depending on the angle and the distance that they're viewing it from, should produce a curved line, which it should look like this. It should produce this on the ground, but this only existed it only exists in the sky optically. The actual elevations that plot out don't change. They only change with by like 6,200 meters over the course of the whole 7 million meter distance. So this means that the observation it's an apparent change in physical elevation. It's not a real change, and the globe demands a real change in elevation. So this
So they're saying that the sun and the moon act just like a plane, an airplane that comes towards you and appears to rise and set and then go away from you. But really, it's just flying parallel above you. No one thinks planes do arcs above them, right? Everyone knows that planes just fly a straight path above you, but in your vision, they look like they're coming and going. And lo and behold, that's exactly what the sun and the moon are doing.
exactly what they're doing. That's exactly it.
Now, the Globers argue that perspective works exactly not like that. It works exactly like that for everything but these things. Remember that, right? These are the exceptions to the perspective rule, as the globularists would say, and we're showing that they're not. They're the same.
Exactly. They'll take the streetlight example and say, like, oh, that's just, local phenomenon. You can't, but like whatever we've heard different, like incoherent things, because to separate the two, you have to just say, it is just because I'm saying it is. There's no rhyme or reason for it. Like why? So like, what elevation does the plane situation stop in the perspective start? Like there's no answer. It either applies to all of it in a different intensities per distance and angular size away from you, or not at all.
Like, so just to go a little bit further, like if you were to do like some trigonometry on the apparent position of that airplane and then go to a second observer and they can do some the same trigonometry on the apparent position of that airplane, meaning using the elevation angle that it appears, do some math, you can calculate maybe the sign, get the distance of that plane. Those two people are going to get a different distance because you're calculating it based on the apparent height. And that's just, again, same thing with the sun and the moon.
Well said. Well said. So here we're looking at, I talked about the distance of that being a diagonal cross of going across America. So this is the path of the shadow here. And then all the eclipse data was here. Actually, I'll put these links in the chat real quick so that people can get them. Here's the links, lads. Let's see here. So we got this eclipse shadow here going across the U.S. So every observer, thinking about that as a plane instead of an eclipse, like Shane was saying, each one of these lads is going to derive a different elevation to that plane. based off of the apparent angle and distance that they're using. They're not going to derive the exact same elevation of the plane across the whole board. That's exactly antithetical to how they mapped out 69 miles per degree for the stars to relate it to a globe. It's directly contradictory. So all of this is all publicly available data. Anyone can go through this stuff, and all the sources are in a Google sheet, or I'm sorry, a Google Drop thing at the bottom of this. So let's see here. So here we have some curves for the change in altitude of the moon over the course of a month. So it doesn't change by much. It changes by like 6,000 meters in elevation or something like that. All right, so how did we get this sun height? We know how we got the moon height. How did we get the sun height? Well, we assume that the height of the moon is fixed at that amount that we derived earlier from doing the tangent of the angle and the distance of the shadow, and that gives us that amount here for the height. So now we have the occlusion angle for the eclipse times the over that distance, and that will give us the height of the sun there. So sun equals the distance to the sun times the tangent of the occlusion, and the distance is of course that shadow length there. So we have that shadow length and then the angle to the occlusion, which creates this congruent triangle here. Now it looks like it looks like it's much higher in elevation than the moon, but we're talking a difference, a change of I think it was 10,000 meters over the course of the whole thing. So they're extremely close together, but for the purposes of demonstrating what it looks like conceptually for the triangles, this one's higher, or it looks significantly higher, but they're pretty close in elevation to one another. So this is how it all works out. This is how we were able to give a altitude for the celestial sphere for the sun and moon. So a way that here's real quick. Here's the data points plotted out over the time of the eclipse and the distance. So what we have is no change in altitude for the sun and the moon. And keep in mind, when because the sun is outpacing the moon and it gets further away, the direction of the shadow changes. So this line actually goes back and forth before it goes all the way over. And you'll see that there's no dip or curve or bending or anything to it. It's basically looks like a straight flat line. And that's indicative of no earth curvature. This should be these lines here that look like this. If the earth were a globe, they would plot out like this. This is the apparent. This is the curve in which we see as derived by the celestial sphere. This is what was mapped out. This is what was actually mapped out in terms of plotting out all those data points and deriving this triangle as it traverses that distance for the eclipse for the entire duration of it.
What an interesting and important conclusion, it seems.
So yeah, it would look more something like this here, plotted out for curvature, and none of that is substantiated. There would be 4 million meters of curvature shown in this graph if the earth were actually curving. If there was any curvature at all to be found, it would exist like this, but it would be in these two sheets and not the.
So using an external reference, all the curvature disappears. Look at that. No way. As soon as you start comparing it to outside of itself, it's gone, meaning it only ever existed in the math.
Well said. Well said. And then we get into, let's see here. So again, using those principles of that relationship of the moon moving at 59.13 something nautical miles instead of the 60 nautical miles, what that would mean is if you were at the equator and you wanted to know what latitude the moon would be at if it was like directly at the horizon, like Polaris would be at the equator, how it's 0, it would be at the moon would be at the 88.7 something latitude. So using that uh, baseline as a distance, you can also calculate the altitude of the moon, which gives a contradiction to the established Keplerian / Newton distance of 300,000 kilometers. The one that we derive comes out to be 274,000 kilometers, and they, it's just, it basically shows that they're the only viable uh, way to describe it in terms of relating it to the celestial and terrestrial spheres, which is, what the globe is built upon. You have to use the celestial sphere radius. You can't use the Kepler and Newtonian distances. They lead to an incorrect triangle. And not the kind of triangle that's like, oh, my spherical excess. It's just dimensionally invalid. It doesn't, it computates to completely different distances. So, all right, so that's the summary and breakdown of the eclipse information. If you guys would like a more in-depth breakdown or to be serenaded by Brian as he reads the reads the PDF that he made to go over it, a video of that could be found here. Get the link, and then we'll go over a couple more things. I know Shane wanted to touch on the 2 pi r situation and coordinate systems with latitude and longitude, which is an extremely important subject and concept to understand if you're going to be arguing for flat Earth and using coordinate systems and maps. This is a very important thing to know. So let's see. You got halfway. You got.
Yeah, you got us cropped. All of us are cropped weird, by the way.
Oh, is it?
Yeah.
Oh, it's off a little bit. My bad. You should have said something. My bad. I didn't read that. I can't read when I'm doing.
You just said I should have said something earlier, but I did say something earlier. I just didn't talk about it.
Don't use my words against me.
Stop arguing with facts and logic. It's not fair.
Yeah, stop doing that. 1 second. I just apologize for that. There we go. That looks better. So sorry about that, lads. All right. So we went over that Eclipse data video here. Put the link in the chat for everyone. So when people are like, how do you explain an eclipse on a flat Earth? How does a flat Earth? Guys, there's no physical elevation change for the sun and moon during an eclipse. That's impossible on a globe. Their whole model is predicated on following the central angle relationship of physical drop of Earth curve. So there can't be also no elevation change. That's preposterous. All right. So let's see. Okay, we got a simulator here from our buddy Goose, who plotted out we plotted out a simulator for all of Brian's data points here. So what we're looking at as this plays out, the flat Earth prediction is on the top half here. So what we're seeing is an observer standing here. As all these angles and distances change, they're deriving the same elevation point for the sun and the moon. Or I'm sorry, as the angle changes over these distances for each observer, there's no elevation change for the sun and moon that's being derived. Now, if we're on a globe, this is what the physical elevation changes would look like. It wouldn't just be an apparent effect. The apparent would just be, our radius of vision's celestial sphere stuff. They've merged the celestial and terrestrial sphere together. So this is what it would have to look like. As this gets further away, this arc has to be physically real to produce the elevation change as per central angle theorem, applying that curvature of the ground to the sky. And it's not, and as we just looked at, it's not represented at all in the data. So there's some really good evidence that the Earth is not a globe, that there is no curvature. And then Shane, if you wanted to, do you have the images for that thing, or I could bring them up if you don't have them? Oh, okay. You want to share?
I got them. Yep.
Okay. You share, and then we'll go over that.
Yeah, nice. I think I want to do whole screen for this because I'm going to be doing just images. So don't share audio.
Don't fall for it. I shared with no audio, and then immediately the first thing I shared required audio.
It's just pictures. That can't possibly happen to me now.
It's a trap.
Right, cool. Ignore all the stuff I have running, whatever. So there's a common misconception over this, right? Like this is essentially a meme that floats around, and they go, look, by misusing this map and not understanding coordinate systems, I can conclusively prove that 2 pi or whatever that pi should be 2 on flat Earth. There's something stupid where they say the actual circumference of flat Earth should be this 39,000 miles because they're saying the distance to the North Pole to the equator is 6214 or 6218 or 6210, depending on what your 69 miles per degree 100th decimal is. But this is not accurate. And I think I saw Jaron take this misconception and just start wackily applying it all over the world and try to get circumference of circles way out here. This is definitely not how this is used. Now, remember, when you're talking about latitude, longitude, it's a curved or spherical coordinate system, as we just went over. Our argument is that sure, there's curvature, but it's all in the sky based on the hemisphere that you observe. None of it's on the ground. None of everything we've ever put forth has shown physical Earth surface curvature, right? We're still looking for it. That's why we're here. We do find, however, through models and ellipsoid models and hemisphere observations of the sky, that you do get sort of curvature, optics-induced apparent curvature of what is parallel. So when we're looking at this meme, we're trying to explain, why doesn't this make sense? Why wouldn't you do this? Well, first of all, this is, a flattened out graticule. So it's not actually the flat Earth map. It's the flat Earth graticule, right? It's this. So it's this exact projection. Remember, this distance is, in fact, in reality, let's say for us within the coordinate system, for them, they think this is the physical 3D curving Earth. Either way, this is a geodesic. This is a curve. 6210 or 6218 or 6214 is literally constructed from their so-called inferred linear relationship of 69 miles per degree. That's how you get this. Linear means the same separation between every degree. That's how they get this curve. That's how they say 69 miles per degree. You can't have it on flat Earth. This is mutually exclusive to a globe. All of that stuff. So that's where this number comes from.
Shane Allen,
as an aspect of the Gleason's projection, or the azimuthal equidistant projection, it is actually, as well as preserving distance from the top, it's a true direction preserving, so it's keeping all the directions. But the most important part we're going to look at, great circle arcs are rectified or shown as straight lines. That means that on both of these depictions, this line and this line are curves. So when we're back to what we're looking at here, and when we're trying to say that this is a radius, sorry, this one. Which one? This one. We're trying to say this is a radius. It's not. This is a straightened out geodesic on this projection. And so, again, I think that what happened was we called attention to that. And I think that you can get like tricky with this and try to display this improper relationship on a slightly different projection, so that you can get away with, well, it's not, this isn't really distorted that way. And like, no, you can't. This is still same projection. It's not quite a flattened out graticule, but it is a Helleric boreal triaxial projection of the same spherical coordinate system of long lat. So it has similar but different distortions of each landmass as it flops out and tries to deal with that same distortion of the spherical on a flat projection. But it's not correcting anything. You're still misusing this curved line as a radius to try and draw the distance between a new circle. The main contention with that is that we don't actually know the distance measured from the North Pole to the equator. We've only ever calculated that based on astronomical latitude. So exactly what we just did. You only ever say, well, based on my latitude and 69 miles per degree, here's how far I am from the center. That's all this has ever been. No one was ever measured directly on the surface. So to correctly do a circumference of 2 pi r to get what the distance between longitude out here would be, you would need an actual along the surface ground distance to be measured, not used on astronomical latitude to be calculated and then used as a radius. Obviously, you can't use a radius, a curved line as a radius. You have to have a straight line. That's just basic geometry. So to use what is in effect this curved line is never going to be a radius. This right here, you can't turn around and say, actually, this is the radius of another 2D circle, even though it's portrayed as a straight line as part of that projection. So that's a sort of a tricky meme that Globers throw around that we should be prepared for when we're trying to use spherical coordinate systems as an argument. Like this is someone not understanding the Gleason's map, because this obviously they don't understand that this line is a curve, or else they wouldn't have tried to use it as a circumference of a circle geometrically.
Can we go back to your triaxial projection there for a sec?
Yeah.
I just wanted to point out its reason for being to the crowd so they understand the perpetration that's going on precisely there. Yeah. Notice that what they mean by triaxial is 3 directions away from north that are going to be deemed south. And that they are not 120 degrees apart. They are necessarily centered. The axes, so to speak, are centered on the continental masses. And that they are proportionally spaced based on, again, spherical graticule generated longitudes in terms of their values. This is how you end up with this projection here. Just thought I'd point that one out to the crowd. That it's far from 120 degrees. You know what I mean?
Yeah.
Thank you. I was wondering what that was supposed to represent with the triaxial. That makes sense.
So what they did was they minimized the distortion within these fields because they separated this out. But what happens is a whole third of the world gets undistorted, and Hawaii's hanging out over here without any projection lines, with no one can reach Hawaii on this map or whatever. But it's fine. They're just showing that you can distort the land masses differently, right? This is commonly used to show how you can distort. How you cannot distort the southern continent sizes on a flat Earth projection. I think that's what this one is, the strength it's used for. But it does have other distortions, because you always have inherent distortions when trying to get that spherical coordinate system to project perfectly onto a flat surface, right?
Entirely.
Yeah, and something to add, if you can go back to the Gleasons real quick. Yeah, the meme or whatever is fine. That would do it. Can you go back to the meme? The 2 pi
the meme.
Yeah.
Yeah.
No, the 2 pi meme. There we go.
That one there, yeah.
I want the
Keeps
pie
opening up in a different window.
Oh, gotcha. All right, so another important aspect of the Gleasons is that while the southern hemisphere looks larger and elongated, the distances, if you use this map correctly, the distance in the north is the same as the distance in the south, although it'll look visually longer and distorted, but that's a feature of how it's projected onto the coordinate system. The length isn't actually different. So when Shane was talking about how just using this straight line as a radius is improper, it's super improper, because this line in the north is the same as that line in the south. It just looks visually distorted because it's a projection. So it's still the same curved line, but it just looks longer because of the projection. So when you properly use this, you could plot out routes in the north over a distance, and you see what that arc would look like using this map. And then when you plot it out in the south over the same distance, you'll get a much visually larger arc, but it's the same distance. So that is a feature of the map.
Yeah, the other thing that's super double dumb to draw a line from here to here and say that this line is the same distance. Since you're passing the equator, this has a different distance scaling than this does. It actually has a different distance scaling all along this, even within the perimeters of this map. So then to say that this is, the radius because it goes this far out and I drew it, you're misusing all sorts of areas of the tool, including the distance scaling, including that that it's a straightened out geodesic. But if you're not taking into account the proper distance scaling, that's why I think when some people try to get sneaky about representing it, they start drawing lines on this exact map with no longitude lines, right? If you just took the lines away from this and you represented this as, say, flat Earth, and you started to do that same projection, it would be less obvious of the distortion inherent in what you're doing. And that's why I say it's a sneaky way to do that same trick.
A little sneak.
Yep, but that's it. Just want to take time to address that one, because people start doing 2 pi r on flat Earth maps and try to deduce that that's the distance between longitude, and that's just category error and absolutely incorrect.
Yeah, you don't want to end up mistakenly arguing a map and model as a physical concept, physical reality.
Don't want to embody reification. No.
I think there was one more thing to show or go over real quick. Screen share. So we have what's called the Celestial Theodolite Measurement Reward Program. We currently have a $300 prize pool. And if you want to make some celestial theodolite measurements, you can get paid for them. But there's a couple of criteria that need to be met. So we went over you need a good east or west peak range. So you can record occlusions or you could record stars emerging. I prefer the occlusions because you get that nice dopamine drip when you're watching the star go into the thing and then you see it touch down. You're like, oh, you get that nice delay. If you do emergences, you're just waiting in the dark and that's it's not as fulfilling, I guess. I don't know. But anyway, they
It's
both
like watching
produce,
your toaster.
yeah, they exactly. These both produce equally valid measurements though, so it's whatever you can get is fine. So if you happen to only live where you can get a Western one, it's all good. You'll just be super bored. I recommend bringing something to do on your phone. Anyway, a occlusion looks a little something like this. This is an example of 39 Aquarii occluding into Pike's Peak here. So we have our star, and then we have the definable peak. So your recording device should be able to make out the star and also make out the peak. And if you're not able to do that based off of equipment or optical reasons or conditions or whatever, a good way to supplement this is show up to where you're going to record early and get the nighttime transition where you could still get the definable images. And then we could use that overlay the next video that you take of the occlusions to produce where the elevate or where the physical peak is. But if you have to do that, you can't move your recording device or change it because it'll mess it up. There's a few things we could do to correct it, but honestly, dude, I'm not trying to readjust your things by rapidity or something like that. I'd rather just, anyway. So that's what it looks like here. So if you have the ability to record something like that at night, you're super eligible here. So all you need to do is have the latitude and longitude of where you're recording from. And then when you start your recording, if your device needs to be synchronized to GPS time, and also you need to know when you started the recording. So most recording devices, when you start a recording, the output file name will be based on the epoch of when you started the recording. So if that's the case for your device, then you don't need to worry about anything. You just need to make sure that your time is synchronized to GPS time, and then you're good to go. We can do everything else after that. And then if you don't know the peak that you're looking at, you can use an app like Peak Finder or the website Peak Finder, the website version. Enter your coordinates. It'll pull up an overlay of the peaks. And when you look at it, you can see you can identify the peaks. It's an awesome app. It makes it really easy. So we just need those three things when you started the recording and let your latitude, longitude, and the peak name, and we can do everything else. Now, the next criteria is if you live in the northern hemisphere, if you are 0 to 300 feet above sea level, then you're eligible for that. The minimum distance to a peak is 10 miles. We took some measurements that were sub 10 miles, and there's not really much of a difference between flat and globe in that regard. So we're looking for further distances out. And suppose you only have one peak available or something like that, but you could do, 10, you could start at 20 miles and then do 10 mile intervals. Every video that you record with your distance interval counts as a separate video. So you can get, up to the whole $300 if you really wanted to in one night, if you got lucky. But so that's how that works for the north. No real distance requirement other than being above 10 miles. And then in the south, there's no restriction on elevation, so it doesn't matter what sea level elevation you're at. We don't have any southern data, so we're not going to be picky. And most people live at sea level in Australia, from my understanding. So any sea levels doesn't matter. We'll take them. And then distance, same requirements as the north, preferably at least 10 miles in difference. And that's pretty much it. That's all the requirements that we need. Everything can be found here on the Celestial Bounty page. I'll put a link in the chat.
Can I show something real quick on the distances ratio? I want to use that the simulator that you can find the ratio where it works and where it doesn't work, or where it's indistinct and where it's distinct.
Oh yeah. Second. So, Celestial. I just had it. Jesse simulator. Talking about this one.
Yeah. So like, there's a combination of distance and height ratio where it's indistinct, where those two triangles, which represent flat Earth and globe predictions, become one. Right? They're indistinguishable from each other. Like if you're at a distance like that, if you find a specific height and distance ratio like that, you can find that that's indistinct. But the further out you go from that point, the further out right you go, the more distinct those two predictions become. So the ratio says up to a certain point, it might be indistinct. Any further than that, and it gets wider and wider apart, easier for us to tell. That's why we say that it's mutually exclusive. But there is, as with any optical arrangement, an actual distance and height ratio where it is indistinct. So just something to be aware of.
Yep, link to the simulator is here, but preferably you just do, random, like whatever distance you get is totally fine. You don't have to worry about simulating or anything. Everything will be plotted accordingly. All right, and I think that's everything. Was there anything else you wanted to touch on, Shane?
Nope, good.
All right,
Once you watch Brian's video.
Yeah, we could close out on that. We could force it or whatever, make everyone watch it.
No, we'll just link it for everyone to watch at their own peril. You did a pretty good job summarizing it, I think.
Oh, yeah, okay. I'm pretty sure I linked it earlier, but here's the link again. So check that out on your guys' own time. It's definitely worth the listen. And then all the data, of course, is down here on this link. So if you click this link, scroll all the way down to Amazing's data, you get a Google Drive link. This will take you to a zip file that has the basically everything that he added to it. I'll show you what's in it. Actually, just click the link. It's going to show it as a zip though. Downloads. So Theo stuff, Eclipse data. So everything that's in here is the Eclipse packet that Brian made. Video from Goose's simulator showing the difference between the two. The Eclipse data from the Excel sheet that Brian used. And let's see. Oh, some responses to the YouTube comments. So there was a couple people that left some comments on the video. Clearly the comments occurred before they finished the video, but Brian was generous enough to take time to write responses to all those things. So if you want answers to some of the questions that were raised in the comments, you can reference the PDFs given here that were made by Brian. So all of that is available on that Google link there. And I would start promoting and like linking this stuff and asking the Globers for an explanation to it. We've been trying to get as many eyes on it as possible, because if we just say it's unrefuted, it doesn't really have any validity to it. But if we put it out there, made it available for as many Globers as possible, and get no refutations to it, then it's more substantial that way. So we're trying to make it as available to everyone as possible and get everyone up to date on the mechanics of the celestial theodolite and the math that we're using and how it all interrelates to the globe model and all of that. Because it might seem a little overwhelming and daunting when we're talking about trig and angles and time and all this stuff. But if you get, getting a little familiar with it, it is the backbone of the globe model. And it's important to know their, to like properly understand their position. Or like what I found is like they don't even understand some of the relationships that we've drawn ourselves from this. So there's a huge gap in between and knowledge there. So hopefully this helps bridge that gap. But if anyone has any questions or comments or whatever, always leave them in the comment section, or you can contact us on Telegram or Discord. Discord would probably be the best way. YouTube comments is a horrible medium to communicate in, but there is a GLOBEBUSTERS Telegram. There's also Witsit's Telegram that we primarily hang out in. So if you have any questions, you can send them in there. We will get back to you. But these are extremely what I would consider important and fundamental concepts to understand, because the backbone of their model is literally subtracting central angle theorem from flat earth angles, which is just, icing on the cake type stuff. So
Nice.
Yeah, right on.
I stop sharing.
What?
You're muted.
Oh, sorry. All right. So coming up for the week on Monday, we have Celestial Theodolite update number 26. That'll be at 8 p.m. Eastern. That'll be on Geo's server. That's Earth Awakenings. That's discord.gg/Earth Awakenings. Tune into that. It's an awesome server over there. Great neutral platform for the lads and ladettes to socialize on. Then, of course, on Tuesday, there will be an Ether Cosmology presentation, very likely on the history of Eratosthenes and Al-Biruni. We're going to get into the relationship of scale invariance and deriving a radius where there isn't one. And because you derived a radius, is it the radius of Earth or is it the radius of your vision? Who's to say? Well, we'll say.
Yeah, indeed.
So yeah, we'll go over that, and then Friday will be Twitter Community Night. Tap in with the boys over on Twitter, see what they're up to. We actually just released all the Eclipse stuff on on Friday, so we'll see if anyone has if any worthy challengers approach for next Friday. And then we'll be back again on Sunday for the next GLOBEBUSTERS, where Shane's going to be doing his presentation on the history of Newton and Uranus and the gravitational potential between them that may or may not have been calculated by several hundred people.
That doesn't sound interesting, but we'll see.
If I keep saying it out loud, it will manifest.
Sounds mighty boring, I gotta say. All right.
Sounds riveting, dear chap. And Stone G, I think you've got the same things coming up that we do, but if you have anything particular going on your Telegram, I think you started doing events and stuff. You got anything coming up?
Well, we're not going to be having it tonight. We're not getting enough people doing their homework week to week, but as soon as we do, I'll let you know for sure. And it's always right after this episode. So when it happens, it'll always be in time for people to catch the show. Yeah, that has to do with resource-based economics, doing without the monetary sequence of value, is succinctly put. And once we get some people with some video homework, I gave them just a couple of questions to ask their friends about choices they'd make in life and that kind of thing based on money. We'll have some more to talk about at the next meeting, and that will be indeed entertaining, I'm sure.
Nice, dude. That sounds awesome and very educational. All right, we will see you guys.